Today our speaker is Zhengwei Wu, who's doing her PhD here at Penn with Salim Hassan, before that she did her undergraduate degree back in Shanghai. So today she's going to talk about some of her work on blind equalization. So, the floor.
Yeah, thank you. Thank you, Ella, for the introduction. And thank you, everyone, for coming here for my talk. The topic I'm going to talk today is computational efficient Toeplitz-Constrained blind equalization algorithm based on independence. And this is a joint work with my advisor, Professor Kassam. So first, I will give some introductions and preliminaries. And then I will talk about the scheme and algorithm I propose for constrained blind equalization. And this will be two aspects. The first is BSS-based algorithm, and another is traditional Pascal-type algorithms. And I will go to these terms later. And third, I will give schemes that will help reduce the computational complexity for these algorithms. And at last, I will give the summary. Okay, this is the introduction. So for blind equalization algorithms, there are two existing schemes. The first is a blind source separation-based algorithm schemes, where the independence relation of the signal source is explored. And the second is Pascal-type algorithms that is based on standard gradient descent that explore the constellation and structural property of the source symbols. And in my proposed scheme and algorithms, I first improve the blind equalization for complex signals and channels as well. And I also improved BSS methods and as well as Pascal-type algorithms using Toeplitz-Constrained and also relative gradient with simple sampling rate. And I propose to implement the algorithm efficiently with FFT and some approximation. So this is the background of blind source separation. So here's the basic problem. We have a vector of source symbols where we have no information about what exactly they are. And we also have a mixture process that is a matrix. We know that it is a matrix, but we have no information about the exact entries of the matrix. But we can see is a linear mixture of the source symbols. That's a vector S here. So the problem for blind source separation is to, based on these observations, we want to have the inverse process so that we know what exactly the mixture process is and what is the source vector is. Since we don't have exact information about this mixture process as well as the source symbols, what we can use, what we know is that the symbols in this source vector is statistically independent of each other. So that is the basic problem of BSS. So in BSS, we want to find a matrix B such that when we apply matrix B to the observation vector, we can have a vector that is a good approximate estimation of the source vector. So in other words, we want to find a matrix B such that B multiply A is approximate identity. This is an application of BSS problem. For example, in a room, we have three groups of people talking, and their talk are independent of each other. And we have three microphones that will receive a mixture of these three processes. So we have no information about what exactly they are talking, and we have no information about how the mixture process is, but we can have the observations, which are three mixtures of the three sources. So the BSS problem is that based on these observations, how do we find the original signal? And this is a similar example of recovering the original signal from mixture. Mm-hmm.
Are you assuming the sources are normal?
What do you mean by normal? Gaussian? No, they cannot be Gaussian, actually. This depends on, if they are Gaussian, then if they mix together, they are still Gaussian. So basically, in the BSS formulation, only one of them, at least one of them, at most one of them can be Gaussian, but they cannot be all Gaussian. If they are not Gaussian, then the mixed signal has no difference between the original signal. So a typical algorithm for BSS is independent component analysis algorithm. That is, we define a function that's a function of the separating matrix, and the function is based on measuring the independence of the separated source. So like here, in linear independent component analysis, we have matrix B such that when we apply B to X, which is the observation, we want to get a matrix Y that contains signals that are independent non-Gaussian signals. They are independent of each other. Any questions? Okay. And a popular algorithm for such BSS problem with independent component analysis is called EASI algorithm. So we can see that's the adaptation for the EASI algorithm. And in the bracket, there are 4 terms. The first 2 terms is for whitening, and these 2 terms are for nonlinear decorrelation. So if B is a good matrix, then the Y, which is a separated source, a separated signal, should be whitened, and they should be independent of each other. And when they are whitened and independent of each other, then the algorithm converges to the steady state, and the terms in the bracket is 0. So the idea of EASI algorithm is based on relative gradient. The general idea of relative gradient is that the change delta B, which is the whole term here, is relative to the current value, because there is a matrix B there. That means if the algorithm is far from steady state, then this term should be relatively large. Then with a relatively large epsilon, we then make a large change based on the current value. But if the algorithm is close to steady state, then the epsilon is small and the change is small. That means we are close to the steady state, and the only change we want to make is slightly based on the current value. And the idea of relative gradient is related to natural gradient, which where natural gradient means that instead of standard gradient, the Riemann structure of the parameter space is exploited to do the adaptation. And this will help make the convergence faster. Okay, I will also talk about the blind equalization model. So in blind equalization, the H here is a channel response, and the S here is a sequence of source symbol. And what we can see is the output of the source symbol, which is a convolution of the channel response and the source sequence. And in blind equalization problem, we want to find the equalizer vector, the W here, such that when we convolve the equalizer vector with the channel outputs, we can get the equalizer output, which is approximation of the source symbol. So ideally, in other words, the cascaded response of the channel and equalizer should have this form, where the D is some delay and the theta is some phase shift. So ideally, the output YK should be the input XK with some fixed delay and phase shift as well. As long as the cascade system has this form, we say that we have an ideal equalizer. Now suppose that we process the channel outputs in sliding blocks along the output sequence in blocks of P plus M. So that means these P plus M outputs are processed in each iteration. And since the channel has order L, these P plus M channel outputs are affected by P plus M plus L source symbols. That means more source symbols contribute to these channel outputs. And if we write the convolution, the vector convolution in a matrix form, we could see that the channel outputs could be written this way, where the H is a Toeplitz matrix containing channel response in each row, with shifted, it is a shifted vector in each row. And the S is just these S elements here. So here we could see that it is a mixture problem, but the H here is underdetermined. That means it has more columns than rows. But we want to find, even if it is underdetermined, we want to find a process that could recover at least part of the elements in S here. So if P is equal than 1, then there is single equalizer output. And in such case, we could only explore the constellation and structural property of the output. And that is what it did in standard Pascal type algorithm. But when P is larger than 1, we will have a block of equalizer output. And in such case, we can explore the independence condition of these outputs, and as it is did in BSS-based algorithm. And next, I will talk about my algorithm that's based on separate parts of that. Okay, first I will talk about the BSBE algorithm with Toeplitz-Constrained. First, consider a special transmission scheme. It is block transmission with some padded zeros. So that means in a source sequence, there are some source transmitted and then padded with L zeros, which is exactly the order of the channel, and then also another block, and then zero block, another block 0. Compared to that, the continuous transmission is that there's no 0. It's just a sequence of source vector. So for the block transmission, since there are some zeros there, we could write the channel output in this way. Since these are zeros, then if we look back at that, we could see that the last L rows, the last L columns will be eliminated because there are L zeros there, so that the last L columns will not contribute to the mixture. So here, that becomes a standard BSS problem where the H tilde is a square matrix. Since it is the first P plus M columns of H, it is a Toeplitz matrix with lower diagonal elements 0. And according to the property of a Toeplitz matrix, we could also say that the H tilde inverse should also have the same structure. So we could exploit such structure of matrix in the adaptation to help convergence. And with such formulation, we want to use an inline algorithm to update B, such that when apply B to the channel output matrix, we will have another the outputs that's an estimate of the source vector. And ideally, the B matrix should approximate the H tilde inverse. So in other words, that ideally B should also have such Toeplitz structure. And in the process of adaptation, we want to keep B in the space of Toeplitz matrix by orthogonal projection. So here's the idea of use easy algorithm with Toeplitz-Constrained. So with the standard easy algorithm, we first update the B matrix. And then knowing that it should have some Toeplitz structure, we will force this to be that structure by forcing the lower parts 0 and then taking averages along diagonals, so that after each adaptation, B should have the Toeplitz structure. And an additional observation is that if we force B to be like zeros and Toeplitz structure, there will be the source will be recovered unbiasedly because there are more non-zero elements in the first cell rows, and there's single elements here in the last row. So an additional step is to add some length constraint to the first sub-rows so that the number of non-zero elements in the first sub-row are at least equal to each other, so that the quality of recovery of the sources will be at least approximately, not exactly the same, but the bias will be not that great. And additionally, since in communication applications, the signal that has been frequently used is QAM, for example, like here, where the complex and real parts and complex parts are independent of each other. We also say that the real parts and complex parts are in phase and conjectural parts. So additionally, the IQ independence constraint could be also added to the algorithm. That means the independence of real parts and complex parts is also used in the BSS algorithm. This is a basic idea. I omitted the details for this IQ constraint for limit of time. When I say phase recovery, I mean that the phase ambiguity could be reduced to a multiple of pi over 2, because if we rotate this pi over 2, we cannot exactly tell the difference. But if the phase ambiguity is reduced to pi over 2, then we could address that with other schemes, which is more easy. And another way for phase recovery is to use hard limiting nonlinearity. We have seen that in the EASI algorithm, there's some G function nonlinearity here. So if we choose a good nonlinearity, for example, the hard limiting function here, the recovered source could also be independent, could also have the phase recovery. Okay, then this idea could also be used for continuous transmission, which is more normal and practical. So for example, if we define a P times P plus M Toeplitz equalizer matrix, like here, where the vector in each row is a shifted version of each other, and the coefficients are from the equalizer vector. Then if we apply such W matrix to the observation vector, we could have a block of equalizer outputs. And the C is defined the multiplication of equalizer vector and channel matrix that contains the impulse response of channel vector. So ideally, the C should have this form. It contains the cascaded response in each row, and the ideal response of cascade system is of this form, which means in each row there is only one non-zero element. And if we apply the ideal W matrix to the channel outputs, we could recover P of the whole source vector. That means at least we could recover P of the P plus M plus L source vectors. But since the S here could be a shifted version of each other, we could only recovering one of the rows will be fine. So here the EASI-based algorithm with Toeplitz-Constrained. Similarly, we also update the B matrix with EASI algorithm. And the Toeplitz-Constrained is false here by taking average along descending diagonals and false the lower parts and upper parts to be 0. And additionally, to have phase recovery, there are also two methods. That is, first to use IQ independence constraint, and the other is to use hard limiting nonlinearity G in the adaptation. And besides this EASI algorithm, such Toeplitz-Constrained could be also used in a broad range of BSS algorithm, as long as it is online algorithm. So after each adaptation, we could always force such Toeplitz-Constrained to help convergence. I will give some simulation results for the proposed scheme. For example, if we define the impulse response of the cascade system like that, and ideally it should have this form with some delay and phase shift, and we use this equation called intersymbol interference as a measure of the performance. So here's a simulation results for block transmission. We could see that with IQ constraint, the IQ constraint is not that much different from the version that without IQ constraint. But with the performance with length constraint is better than the performance without length constraint, but only Toeplitz constraint. And these two are much better than the original easy problem. So that means with structure constraint, we could make the convergence of the algorithm much faster and improve the performance as well. And this is for the continuous transmission. Here, these three lines are the very popular BE algorithm, like CMA, MMA, SCA. And these three lines are our proposed algorithm. The blue and red line here are the one that with and without IQ version. And this cayenne line is use a different nonlinearity. So we could see that the performance of these three curves are comparable, but they give faster convergence than the standard BE algorithm. Okay, next I will talk about the Pascal type BE algorithm, which is based on relative gradient. That means to explore the structural property of the source symbols. For example, that YK is the output of equalizer. So ideally, we want it to be an estimation of the source symbol. For example, GY is a function of the equalizer output, and it is based on constellation. So an example of such Pascal type algorithm is constant modulus algorithm, where the Xi function has this expression. So that means we want to minimize the deviation of the output modulus from a constant. And the YK could be expressed this way, where corresponds to the previous case. That means P equals 1. We have single equalizer output. And in standard Pascal type algorithm, the standard gradient descent is used. That means just take derivative with respect to the vector and then do steepest gradient descent. And ideally, at a steady state, this part should be 0, right? And it could be shown that, in fact, at a steady state, we have that the expectation of the cross correlation is 0. And that is called Pascal condition. That means at a steady state, the output and the nonlinearity of output, their cross correlation is expected to be 0 with any time lag. So with that Pascal condition, we'll explore to how to use that to improve performance. Similarly, we also define an equalizer matrix, which in each row, the equalizer vector is contained. And if we apply the W matrix here to the channel outputs vector, we will get a block of equalizer output. Here, this is a longer vector of channel outputs. I use tilde because I want to tell the difference between my scheme and the standard BE scheme. And especially when P equals 1, then they should be equal to each other, because then we will have only one equalizer output. So now, since we already have a block of equalizer output, we could explore the constellation property of each of them. And now we can define an average cost function, which is a summation of them. That means the summation of the original Pascal type cost function, right? And that would be a function of the matrix W. And since matrix W here contains the equalizer vector in each row, that could be also equivalently as another function of the equalizer vector. So now we have three versions of cost function. The first is a cost function of the equalizer vector, and that is based on single output. These two, the second is also a function of equalizer vector, but it is a function based on multiple outputs. And for this function, matrix, a function of matrix, that is also a function based on a block of multiple outputs. So for all these three functions, we could use standard gradient as well as relative gradient. After doing the mathematical implementation, we could see that with standard gradient, the three functions they are not that different from each other because it's just a standard. But this one is just standard Pascal, and with the summation, it could be seen as the average version of that. And for these two functions of vector, if we use relative gradient, the result is not reasonable. So that actually relative gradient cannot be used for vector adaptation. But for the matrix adaptation, if we use relative gradient, the performance will be greatly improved. So basically, with relative gradient for matrix, we have the two-step adaptation. The G here is just a derivative of the cost function that defined for a certain Pascal type algorithm. And we could see that in the first row, the relative change matrix that before the W matrix here contains the cross-correlation terms of G and Y. If we recall, we could find that the GY cross-correlation term is just exactly the terms in Pascal condition. So that means we use the Pascal condition that is should be 0 at the steady state to measure the relative change. And this is similar to the previous BSS-based algorithm. So if GY Hermitian is large, that means we are far from steady state, and the change should be large. If it is small, then the change should be slight. And with this adaptation, the second one is to force Toeplitz-Constrained by taking averages along diagonal, and that could be proved to be an orthogonal projection onto the space of Toeplitz matrices. Here is an example of the standard CMA and our block relative gradient version of CMA. So we could see that the red curve is a standard CMA, and the performance of our algorithm depends on the value of P. So here, the equalizer order is M equals 25. If we take P, approximately half of that, the performance is really good. And if larger or smaller than that, maybe the performance will degrade. For this black curve, although P equals 12, but if we don't force Toeplitz-Constrained, that means we don't have second step adaptation, then the performance is not good either. So to conclude that means if we have a P that is approximately half of the equalizer order and use the two-step adaptation, the performance will give faster convergence compared to standard algorithm. So for both of the two algorithms I mentioned, we could see that they have similar form. That means in the first step, we do matrix adaptation, and in the second step, we force Toeplitz-Constrained. The difference is that in the first T-EASI algorithm, the independence is used. But for the second algorithm, the starting point is the structural property of the constellation. So for both algorithms, we could write it in a symbol form like that. And the only difference is the U matrix here. So here, it is a matrix adaptation, but we could also see that in each row of the matrix, the equalizer vector is contained there and repeated in each row. So in fact, the next question is that can we come up with a way to update the vector only, which may reduce the computational complexity? So in fact, it can, and the equivalent computational efficient adaptation should be of this form. And the phi matrix here contains correlation terms of the U. And I will show how to get phi matrix from U matrix. For example, the U matrix is a square matrix here. And if we take summation along descending diagonals, we will have 2p minus 1 terms there, right? And we can also define some extra terms beside the 2p minus 1 scope. And then by mathematical deduction, we could also see that the phi matrix is exactly a Toeplitz matrix containing these summation terms. That means from 0 to m and minus 1 to m minus 1. So in this matrix, 2m minus 1 terms are contained there, among which 2p minus 1 are from here, and there are some extra zeros there. So it turns out that we could do vector adaptation in this single step, which will reduce the computational complexity. And a further thinking is that could we reduce computational complexity even more? And the answer is yes. So there are two ways in this computational complexity reduction. The first is you implement the algorithm with fast Fourier transform. And another is to make some approximation of terms in this phi matrix. So for example, with the block radial gradient Pascal algorithm, we have that the equalizer output is a convolution of channel outputs and equalizer vector, right? And the RG, since the RK, since the terms are the summation of descending diagonals here, we could also get that with some convolution of G and reverse order of Y. And additionally, for the phi k WK, the multiplication there, since the phi k is a Toeplitz matrix containing a single vector, shifted vector in each row, the multiplication could also be obtained with some convolution. So for any of the convolution thing, we could implement that with fast Fourier transform, which will give computational efficiency. And another step is that to use approximation for the cross-correlation terms. For example, this is the UK from previous iteration. And in our algorithm, we want to, if we have a new updated equalizer, we need to update all the terms in U. But actually, since the difference between two iterations are not that much, we could use some approximation from previous iteration. So actually, when we have a new vector, we only need to get a new only single one equalizer output. And for the other terms, we could take from previous iteration. And the cross-correlation terms could be like with this new output and with other old outputs from previous iteration, so that only the first row and columns need to be updated, and the other terms could be taken from previous iteration, so that it will save much computation. So with all these computational complexity reduction scheme, we can save the computational complexity and increase convergence as well. And increased convergence will save the data that used to train these equalizer vector. So at last, it is a summary. In this project, I explored two kind of algorithm. The first is based on blind cell separation that explore the independence of symbols and to force Toeplitz-Constrained in the adaptation. And the second one is Pascal type algorithm, use relative gradient and also force Toeplitz structure during adaptation. And at last, both of the algorithms could be more efficient with some FFT and approximation scheme. Okay, thank you. Any question?
So what happens to your algorithm when you get the length of the channel wrong?
Long?
How much is it? Yeah,
Oh.
that can happen, right?
Actually, when the channel is longer, we need a longer equalizer vector to equalize that. So the problem will become more difficult for both of the original original BE algorithm as well as our algorithm. Yeah.
What I mean is how sensitive it is to the mismatch of you estimated the length of the channel wrong. The channel is longer than you thought, or it's actually shorter. Mm-hmm. Is it how robust it is to that?
Actually, here's the problem. Because at first, you have no information about the channel, right? You have no information about channel state. So a safe way is to use a comparatively long equalizer so that you could at least guarantee that the performance is much better than using a short equalizer, right? So if you start from a longer equalizer, then you construct the equalizer matrix in a certain way, then the performance could still, the algorithm still works. But it may take like longer sequence to converge, and the convergence start may be not that much good.
What if you plug this structure, the other structure that are preserved on their index? The lumpy structure.
Sorry, could you?
Can you replace the Toeplitz-Constrained with other structures that are preserved on the matrix index?
You mean other structure than Toeplitz structure? Actually, we have been thinking that for a certain transmission scheme, maybe we could explore circulant matrix or could be seen as a special case of Toeplitz matrix. But I think the structure of the matrix depends on what kind of scheme you use to transmit and what kind of scheme you use to process the data. So in our scheme, we transmit the signal with we process the channel outputs in with one symbol shift. So that's give the result that the equalizer matrix turns out to be Toeplitz. But if you use other scheme, maybe that will lead to another kind of structure that you may explore. Mm-hmm.
A quick question. In what application settings would these kind of BE algorithms be advantageous?
For example, there are some people at the transmission side, and there are another people at the receiver side, and both of you want to have a more clear information about what the channel looks like, but you don't have exactly information about it. So the transmitter will transmit some signal, so that the receiver side will know that, oh, okay, these signals are independent of each other, but I don't know what they are transmitting. But based on their observation, I could explore such process so that after using these independence condition or constellation condition, they will try to recover the channel state and then use that to maybe improve transmission or have a better idea of what's that.
There's a speaker in the other hand.
Okay, thank you.